Hello everybody and welcome to Module 2. Today we're going to cover the first half of Module 2, so we're going to go all the way to example 2.2. Remember, this is a video, so make it work for you. If you need to watch something again to understand it better, do that. Take notes as I cover information and work all the examples I present to you and all the extra practice problems I present to you as well. Now, what are we going to cover in this module? This module is about energy, heat, and temperature. So we're going to cover energy and heat, the nature of scientific law, the first law of thermodynamics, units of heat and temperature, the calorie unit, how we measure heat, and then we're going to talk about the calorimeter and how we do problems with calorimetry. So that's what we're going to cover in this module. Let's see if I can make this smaller. Okay. In module 1, we learned that chemistry is the study of matter. So chemists study matter, and matter was anything that took up space and had mass. If you remember that, you should remember that. And it also studies any changes that substance goes through. So maybe a state change from gas into liquid into a solid and back to liquid and to gas. So state changes, that's something that chemists study. They also, of course, study chemical reactions when substances change all the way, not only physical changes, but chemical changes that are not very easily reversible. You're going to learn all about that. So substances and the changes that go with those substances. That's what chemistry studies. Anytime that matter goes through a change, that change has some kind of energy related to it. This energy coming into the system or going out of the system. So energy is being released or is being taken in. So what is energy? If we need energy for changes to occur, what is energy? You may have an idea of what that is already, but let's look and see what the scientific definition of energy is. Energy is the ability to do work. And you may say, what is work then? In a minute, I'm going to tell you what work is from a standpoint of science. Okay? So the definition of energy is the ability to do work, and you need to know that. There are all kinds of energies, but chemists study thermal energy, nuclear energy, chemical energy, of course, kinetic energy and potential energy, and ionization energy. Those are the kinds of energies that chemistry is concerned with. But there are other kinds of energy that are studied by other kinds of scientists, like physics. If you study physics, you're going to look at mechanical energy and all kinds of other energies. Okay. Now, we said that energy was the ability to do work. So what is the definition of that work? Work, basically, W here for work, is a force times the displacement that force applies. So this is the mathematical equation that allows us to calculate work. And you will not need to do that for chemistry. You do that in physics. So, force acting upon an object to cause a displacement, that's what work is. The wall right here is not moving. If the wall is not moving, there's no work done. I know that is very counterintuitive. You may think that's kind of weird because you can see the two men there pushing on the wall. They're sweating. They're exerting energy trying to move that wall. But the wall is not moving. There is no displacement. Even though there is a force applied to the wall, there is a force, but there is no displacement. There is no work done on that wall. Why? Okay? So let's continue with this. For work to occur, there must be motion. If you don't move, you don't have work. That's your definition. Energy, in other words, is essentially the ability to cause motion. Because energy, if you remember the definition of energy, is the ability to do work. And work translates into motion. If you don't move, that force is not causing work. So energy is the ability to cause motion. Keep that in mind from now on, okay? Energy causes motion. One of the examples you're probably most familiar with is burning logs in a campfire. So you probably have gone camping. You're familiar with campfires, or maybe you have a fireplace in your house, okay? But you're burning logs. So here you have some logs. There is fire. You started a fire. That's a combustion reaction, and you're going to be learning about the different kinds of reactions pretty soon. Not yet, but you're going to get there. And you're going to be looking at how to write reactions in a chemical way. But for right now, you don't have to worry about that. But just note that is a combustion reaction. You have the logs is an organic material that has carbon and hydrogen combined with oxygen to produce carbon dioxide, water, and release of energy. That H stands for energy, and that means change in energy. The energy, you're going to learn that energy is not created or destroyed. It can only change forms. Was there all along, is in the logs. The bonds between the atoms in the matter that makes up the log, so the carbon and hydrogen, okay, between them, X and Y means that there's several of them. Different substances have different numbers of carbons and hydrogens. So the bonds between them have energy. And when you break them, you release energy. Okay? But you're going to learn that in a lot more detail in modules to come. But basically, you're burning the logs. Here are your flames. The flames cause the air around it to move. There is smoke that goes up, little specks of matter that's flying up that is burning. Water vapor gets released from the logs too, moving up. So there's all kinds of things that are moving. And moving means that you have motion. Motion means there's energy being released there. Okay? Now, the definition you need to know for heat is right here in this box in red. Heat is transferred as a consequence of temperature differences. If you don't have temperature differences, you don't have heat transfer. Transfer is a movement. Keep that in mind. So here's another definition. Heat energy is a form of energy transfer, so it moves from one place to another. But unlike temperature, because they are not the same thing, and we're going to go into more detail how they are not the same thing in science. So energy refers to energy. Heat is energy inside the system. It was inside the log. And that energy is being released. It was inside the log. It's potential energy. You're going to see that in a minute. And it becomes kinetic energy, which is energy that causes motion. Motion of little particles that go up in the smoke, or the atoms of water that are getting heated and move up into gas form from the log. So all of that is a form of energy. Heat is energy. Please know that, okay? Now, as I said to you before, for heat to move, you need to have changes in temperature. Heat always travels from hot to cold. Always travels from hot to cold. And you need to remember that. If you don't have a difference in temperature, there is no heat. There is no movement. There is no movement of molecules or particles. And I know sometimes that is kind of a strange concept to think about that. In science, sometimes you have to think for a minute what it means. You already know, for example, that air masses, when they create wind, they are moving from a high temperature to a cool temperature, and they are moving, creating those winds. So it's a little bit like that. Think about heat as movement from a high temperature to a low temperature. There is no difference. There is no heat transfer. You need difference in temperature for the heat to transfer. You need to be able to give me examples of heat transfer. Water boiling, air moving, the wind, the smoke coming out of the logs that we saw a minute ago from the campfire. So not only do you need to know what heat is, but you need to be able to give me examples of heat transfer. Now, I said to you that temperature and heat are not the same thing. In science, they are not the same thing. I know that sometimes when we talk about things, we make the mistake of using those two words interchangeably, but they are not the same thing. And you need to know that. They're closely related. You're going to see in a minute a formula that puts the two of them together, but they are not the same thing. Changes in heat, okay, cause changes in temperature. And you're going to see this in a minute when we study the thermometers and how thermometers work. Heat is energy. Heat is the kind of energy that we call kinetic energy. And in a minute, you're going to have a definition for that. But kinetic just means moving. So it's energy that moves or causes a movement. And is the energy that's contained in a substance. Adding heat to a substance can change the temperature of the substance. That makes sense. Usually when you give heat, when you give energy to a substance, the temperature goes up because temperature is just a measurement of the expansion of the atoms or molecules of a substance. You'll see this in a minute how it works. But basically that's what you're doing when you're looking at a thermometer. When you're recording the temperature, you're seeing how the substance moved up or went down because the heat was making those atoms and molecules move. Okay. Temperature is an indirect measurement of heat. We said that there was an equation that relates the two of them, but it's not heat. It's a number that represents an average kinetic energy for the substance molecules. That's what it is. In your mind right now, you don't have to memorize all of this. You need to remember they are not the same thing. Heat is energy, is kinetic energy. Temperature, on the other hand, is a visualization. So you can see how the atoms and molecules move because of the presence of heat. That is an average of what happens to those atoms and molecules. So if I ask you a question like this, which object contains more heat? Remember, heat has to do with how atoms and molecules move. Okay, a boiling hot cup or a massive iceberg? You can pause for a second and think about this. Well, it goes about your instincts, but an iceberg would have more heat because heat has to do with the movement of molecules or atoms. And a massive iceberg has more atoms and molecules than a cup of tea. So the more molecules moving, the more energy you have there. The more energy you have, the more heat you have. So in your head, keep in mind that the greater the mass, the more energy you have present there. Now, temperature follows your instincts. The boiling water and the tea has a higher temperature than the iceberg. So heat and temperature are not the same thing. Now, before we look at the first law of thermodynamics, you need to know what a law is. Hopefully you know these from physical science and from biology. You should have some inkling of the difference between a theory and a law. You already know that science works with scientific hypothesis. You start with a hypothesis. Usually a scientist looks at the world, sees something that is interesting to them, wants to study it, does observations, reads about it, learns about what other scientists have learned about it, and then come up with a plausible explanation for whatever they are researching, whatever has become interesting to them. Okay, so they're making a prediction. Hypotheses can be changed, revised, and then you create an experiment as a scientist to prove your hypothesis. Sometimes the hypothesis proves to be true, and sometimes it proves to be wrong, and you start all over. Okay, but what is a theory and a law? Well, law summarizes a set of observations about natural phenomena. That's what it is. A theory explains why natural phenomena occur. So we're going to look at the first law of thermodynamics. Usually it has to do with how long it has taken, how many times has that experiment been done over and over and proven it to be true. You move from theory to law. That's what happens, okay? If something keeps happening the same way and all the scientists agree on it, it becomes a theory. And if over time that theory proves to be true, so even though maybe we have new instruments that help us measure things, we have new discoveries, but it still holds true, then it becomes a law. Now, the first law of thermodynamics, it has to do with energy. Energy cannot be created or destroyed. It can only change forms. That's what the law says. And you need to know what the law says. So if I say to you, what does the first law of thermodynamics say? You would have to say, energy cannot be created or destroyed. It can only change forms. So there was energy before. It's transformed into a different kind of energy after. It was not destroyed or created, it just changes forms. That's what the law says. The total energy in the universe does not change. The amount does not change. It just changes forms. Now, we're going to learn about kinetic energy and potential energy in a minute. I'm going to give you the definitions. I'm going to tell you what they are right now. But know that the total energy in the universe does not change. You have potential energy and kinetic energy. Together is the total energy that you have. So energy can exist as potential energy or kinetic energy, and they change from one to another. Okay? Potential energy is energy that has potential to do movement. It's not creating movement, but it's there. It's not creating work yet. Okay? It's not doing any work for you. Kinetic energy is energy in motion, so it creates work. We use kinetic energy to make wheels turn that can do anything for us, like create electricity, for example. Okay? So your potential energy, as I said to you before, all substances have potential energy. Substances have mass. They're made out of atoms that create molecules. And those molecules between the atoms, you have a bond. You're going to be learning about bonds pretty soon. But in those bonds, you have energy. So that energy is there in the bonds. So when you break bonds, you release energy. When you put bonds together, you need energy. So you're going to learn all about that. But basically, you have energy coming in, energy coming out. Back and forth, back and forth. But the total amount of energy never changes. Okay? So as we learned before, a fire is a combustion reaction. You have an organic substance with carbon and hydrogen combining with oxygen in the atmosphere. And when they burn, okay, that's a combustion reaction, you get carbon dioxide, water, and a lot of energy is being released. Here you go. Heat that makes water that was in the log move up in the form of vapor water. Maybe little specks of things fly up because the air also gets energy and they move faster and it moves up. Okay? So there you go. So you do need to know the definition of both potential energy and kinetic energy. Potential energy, what is that? I said to you, potential energy is the energy stored in the bonds between atoms or molecules, or both. Okay? So in the bonds have energy that is stored. It's not creating motion, it's not being used for motion, it's not working for us, but it's there. It's there waiting. Anything that can burn has potential energy. Anything that can undergo a chemical reaction, like batteries, has potential energy. Food that we eat has potential energy. We're able to break down macromolecules if you have done biology already, which you should have done biology before you take chemistry. You already know that we break down macromolecules to make smaller monomers, okay, that later on we use for building our own cells and tissues and organs and so on. But it also releases energy. Okay? All substances have potential energy because all substances are made out of atoms and molecules that have bonds between them. As simple as that. Potential energy. Potential meaning it's there in waiting, not doing work for us, but it has the potential to do work for us. So the other kind of chemical energy you're going to be learning about is kinetic energy. And if you do physics, you're going to see them again. So kinetic energy is energy that is already in motion. And remember that motion translates into work. If you remember from when we talked about work, what that was, or energy is the ability to do work. Work translates into being a force that creates a displacement. So there has to be motion. If you don't have displacement, if you don't have motion, you do not have work. So kinetic energy is energy that is in motion. And the example we have seen so far is heat. Heat is kinetic energy. Great. And remember that if this is not making sense to you, you can watch the video again, you can read the book, you can ask me questions when we meet virtually. So ask me questions or you can email me. So let's look at these units for measuring heat and energy, because we said that energy is a form of, heat is a form of energy. Heat is kinetic energy, so they have the same kind of units. The units that we're going to be using in the metric system is the joule. And if you do physics, you're going to work with the joule quite a bit. You also need to remember that heat and temperature are not the same thing. This is the formula I said to you. There was a formula that related the energy, the heat with temperature. So this is it. Heat, Q, stands for heat, equals the mass of the object we're studying, times C. C is the specific heat for that substance, okay? And the delta, anytime that you see the delta, that means a change in temperature. So final temperature minus initial temperature. And you're not going to use this equation yet, later in a different module or later in the chapter. I don't remember if it's in this chapter or later on, but you will eventually use this equation, but not today. So that's how they are related. They're indirectly related. Heat causes changes in temperature, and you're going to see how this works. Now, thermometers. You know that we use thermometers to look at temperature. What is a thermometer? Well, a thermometer is just a glass container that has a liquid inside of it. Usually is alcohol that's been dyed. This one is red. Sometimes it's blue. It's a different color. There used to be mercury, made out of mercury, but mercury is poisonous, so we don't make them out of mercury very often anymore. We use dyed alcohol. And then they have all these little lines. The units for temperature are different units depending of in what country you are in. Here in America, you use the Fahrenheit. In Europe, we use the Celsius. And we're going to be using the Celsius mostly, and also the Kelvin for this course. You're gonna have to change Fahrenheit into Celsius and Kelvin. You're going to learn how to do that in this module. So you have a scale, and remember that anytime that you have a new apparatus like this thermometer, you need to look at the scale. You need to study how many lines do you have, how many little lines you have, and what units. The thermometer will tell you if it's in Fahrenheit or Celsius or what it's measuring. But what happens when you have a thermometer is that heat, which is energy, okay, is being transferred through the atoms and molecules that in the air will heat the glass in the thermometer, and it will transfer into the liquid inside of the thermometer. So now the heat, that motion, okay, makes the molecules and atoms right here also vibrate. All molecules and atoms have some kind of vibration. You'll learn these if you haven't learned that in physical science, that solids vibrate a tiny bit, liquids a tiny bit more, and of course gases, the atoms and molecules in gases go crazy, move all over the place. So anyway, the heat heats the atoms and molecules here, and they vibrate, they expand. Okay, the only way for the atoms and molecules to expand is up through the tube inside the glass. So when you are reading the temperature, what you are actually reading is the displacement of the substance because of heat. So the temperature is just a visual it helps you visualize the amount of energy that is present in a way. Okay, you're not measuring the heat itself because it's very hard to measure heat itself, but you see what heat can do when it heats those atoms and molecules, which is make them move. And when they move, they expand. And when they expand, you can read the temperature. And you already know that the more heat, the more temperature. Okay? So that's what it is. Cold substances, atoms, molecules very close to each other, vibrating a little bit, but as they are heat and gain energy, they move faster and they're moving far away from one another. To move far away from one another, the only way for them to do that is to go up inside the thermometer. Now, you will do an experiment in which you're going to have to calibrate your thermometer. So in figure 2.1 on page 42, they tell you how a thermometer is calibrated. You put the thermometer in a beaker, in a container that has ice. To be able to calibrate anything, you need to go with physical properties of water that you are familiar with. You know that water freezes at 0 degrees Celsius, okay? And you know the water boils at 100 degrees Celsius. And if you don't know that, you're going to have to memorize that for this course, not only in Celsius, but in Fahrenheit and Kelvin as well. So you leave the thermometer in the ice water, and you leave it there for a few minutes until the liquid, the alcohol, stops moving. Okay? Where it stops, that's going to be your 0, because you know that ice, solid ice, is at 0 degrees Celsius. So if it stopped moving there, that thermometer now is at 0. Okay? Now you put the thermometer in boiling water. Boiling water means 100 degrees. Water boils at 100 degrees Celsius, okay? And you wait until the alcohol doesn't move anymore. The dyed alcohol here, red, stops moving. When it reaches this stop, it doesn't move anymore. You know that that has to be the 100 degrees because the energy is being transferred from the water to the glass, from the glass to the molecules of the alcohol, and they are expanding up. as much as they can. How much do they can? Well, as much as the ones in the water could. And you know that water boils at 100, so that's also at 100 Celsius. So now you have where the 0 belongs and where the 100 belongs. And then you put the little lines in between to make it 100 little lines for degrees. Each one is 1 degree. You don't have to do that. You do not have to draw the lines in your thermometer. The lines in your thermometer that comes from the factory already has the lines. The problem with the thermometers that you have is that sometimes they're not calibrated very well. So you're going to have to find the true 0 and the true 100 in your thermometer. That's what you're going to be doing for your lab. So let's look at the different temperature scales. You're familiar with Fahrenheit. That's what you use here in the United States. You use Fahrenheit. In Europe, we use, and the rest of the world, we use Celsius. And then we have the Kelvin. And you're going to learn that the Kelvin is the absolute scale for temperature. We're going to see what that means in a second. But you need to know both the boiling point and the freezing point of water in Fahrenheit, Celsius, and Kelvin. Okay? 100, 0, 373, 273, 212, and 32. You need to know these. Okay? So I should say water in here, not weather. The water, when it's boiling, okay, it doesn't matter if the water only has a few bubbles showing you that it's boiling or it's roaring boiling. As soon as you see little bubbles, the water is already at 100 degrees Celsius or 373 Kelvin or 212 Fahrenheit is already boiling. So you don't have to have roaring boiling water for it to be boiling or be at that temperature. As soon as you see little bubbles, it's already at that temperature. And the same thing for the freezing temperatures, okay? 0 degrees Celsius, when you see a tiny bit of ice, if you have a combination of water and ice, if you have ice present, that water is at 0 degrees Celsius, even if you have water present. Or if you're talking about Fahrenheit 32, or you're talking about Kelvin 273. So you don't have to have a block of ice for it to be at that temperature. Tiny bit of ice means it's already at 0. Okay? Now, let's talk about the absolute temperature scale, because we're going to be using Kelvins a lot this year. So when we're talking about Kelvins, we're talking about the absolute scale, absolute temperature scale. Nothing can be colder than 0 degrees Kelvin. We have not even been able to reach 0 degrees Kelvin. We have been able to reach like 0.0001 Kelvin. So very close, we call it 0, but we have not really been able to reach that 0 degrees Kelvin. That's why it's called the absolute scale. And we're going to be using this scale to do math because sometimes we have to divide by temperature. And you already know that we cannot divide by 0. When you divide by 0 in math, we cannot divide by 0. Okay? So because Kelvin cannot reach 0, you'll never have a 0 Kelvin. We can use that temperature to divide with temperature. Okay. Let's see if I'm going to remember everything else. Yes. You're going to have to know how to change from Celsius into Kelvins. In a minute, I'm going to give you the equation. But I want you to notice this number right here, 273.15 units. This right here is not infinitely precise. When we were changing from one prefix to another in the previous module, when we were saying that in 1 meters we had in 1 meter we had 100 centimeters, so that 100 was precise and you could have as many significant figures as you wanted. When you are using the equations I'm going to give you next to change from Celsius into Fahrenheit, this number is not infinitely precise. This one has 1, 2, 3, 4, 5 significant figures, or it ends in the 10th position if you're doing addition or subtraction with significant figures. So it's not infinitively precise. You need to take into account the position or the number of significant figures. Okay. Now, you are going to be doing experiment 2.1 on page 43, and it's going to be about calibrating your thermometer. Please be careful, read all the instructions, always read the instructions. This is like cooking, so when you're following a recipe, you have to be very careful or your cake does not turn out the way it's supposed to turn out. So don't skip any steps. I advise that you read everything once first, and then read it again, and then start working on it. Okay? But read once without doing anything, just read it. But you're going to calibrate your thermometer and find the true 0 and the true 100 for your thermometer, because I said to you that thermometers that come from the factory a lot of times are not calibrated correctly. So you need to learn where the true 0 and the 100 is for your thermometer, so when you do experiments in the future, you have the right numbers. Now, you may have done this already in your math course, so it might be a repeat for you, it might be new to you, but I'll explain it to you. We're going to do examples, so it's not too complicated. So how Celsius, Fahrenheit, and Kelvin are related to one another? We have equations that help us convert from one temperature scale to another temperature scale. Celsius to Fahrenheit, and from Fahrenheit to Celsius, or from Celsius to Kelvin. So you have different equations that you can use. You just have to use the right one. These two really are the same. It's just that it's been rearranged. So you can just memorize one and learn how to rearrange it, or memorize both of them. If you go into science, I would advise for you to start memorizing equations. If you're not going to go and major in science, when you go to college, you're not going to major into science, and your parents are okay with you keeping a page of equations, I'm okay with it too. You can keep a running page of equations. Not explanations, not how to use them, but just the equation itself. You can have a page of equations for your practice problems and even your tests, okay? So it's not that I need you to memorize this, but if you go into science, start learning this, because not all professors in college will allow you to have a running page of formulas. So how does this work? If you want to know how many Celsius you have, given an amount of Fahrenheit, you would put the amount of Fahrenheit they give you here. You would take away 32 and then multiply it by 5/9. So this is a fraction, okay? 5 divided by 9, that's just a fraction. If you want to know the number of Fahrenheit given your Celsius, you put the number of Celsius here, multiply it by 9/5, and then add the 32. If you want to know the Kelvins, and you have the Celsius, then you add the 273.15. And remember I said it was not exact. And this is addition, so you're going to have to stop in the 10th position because you're not going by number of significant figures, you're going by position. Okay? So you need to check the position of this one as well. If they give you Fahrenheit and you want to know the number of Kelvins, you're going to have to stop first by the Celsius, find the Celsius first, and then use this equation right here to find your Kelvin. How does that work? Example 2.1. Let's look and see how this is done. Remember that you need to be working on the problem as well. So I'm going to explain it to you, but you need to also copy how it's done. And then we're going to do extra practice problem number 1. But it says a student uses a Fahrenheit thermometer to do a chemistry experiment, but then must convert his or her answer to Celsius. If the temperature reading is 50 degrees Fahrenheit, what is the temperature in Celsius? Okay. Of the two of them, I hope you can see that they want the temperature in Celsius and they give you the temperature in Fahrenheit. So you're going to have to use this equation right here to find what they are asking. Let's see the second part. We usually say that room temperature is about 25 degrees Celsius. What is the temperature in Fahrenheit? So now for this one, they want the Fahrenheit and they give you the Celsius. You're going to use the second equation right here. You see how this works? Use the correct equation to find what they are asking. So let's go here and get to the whiteboard. Let me get the pen. So the first part of the example, let's see if I can get my white here. They want to know the number of degrees Celsius that you have in 50 degrees Fahrenheit. So you copy the equation, you start with the equation. It says that's the number of Fahrenheit. I'm going to put it right now for right now, minus 32. Okay, this is your equation. I'm going to erase for a minute. Oops, I didn't want to erase everything. Let me put it again. Degrees Celsius equals 5.9 Fahrenheit minus 32. Okay, I just wanted to erase a little bit. Okay, this is your equation. Now, they gave you the Fahrenheit. So put the Fahrenheit in the appropriate place in your equation. And that was 50. Okay, so the equation now is correct. Everything, first you do what is in the parentheses, so 50 minus 32. Then you're going to multiply whatever this is times 5 divided by 9. And you can use your calculator and open parentheses to do that. But if you do that, your answer should be 10.0 degrees Celsius. Why this amount? This is precise. That's infinitively precise. If you're part of the equation and I didn't tell you that you needed to take into account the number of significant figures, the fraction is also precise, okay? You are going to go with the precision that was in here, okay? The precision that was in your Fahrenheit. So this ended in the 10th position. Your answer needed to end in the 10th position because this right here and this right here are infinitively precise. Okay, so now yes, I can erase this and this is done. So for the second part of the example, they were asking for the Fahrenheit. So you always start by writing the formula. Fahrenheit equals 9/5 the number of Celsius you had plus 32. Okay? So once again, let me make sure that I'm not erasing everything. You are going to put the information they gave you in the appropriate place in the equation. They gave you 25 degrees Celsius. So put that in there. Okay? This is what they gave you. So as you can see, you need to do this part first, okay? 25 multiplying 9 divided by 5, and then add the 32. So do that, and you see that your answer is 77 degrees Fahrenheit. That's your answer. Why 77? Well, this one right here, when you multiply and divide, you went with the number significant figures. I said the fraction and this number don't count. Have as many as you want. It could be 0.00000, 0.0000. So you can add as many zeros as you want after the decimal point because they are infinitively precise. So you had to go with the precision of the number they gave you. And that has two significant figures. So you give me two significant figures as well. So now that you have done the example, you're going to do number 1 of the extra practice problems. And as I said to you before, read it really carefully. I'm going to give you the answer, and if the answer is correct for you, you move on. If you don't get the same answer, then you can see how I solve this. So number 1, you should be getting 1.4 degrees Celsius. You got this, move on. If not, check to see how this is done. So let's see. They want you to convert 34.5 degrees Fahrenheit into Celsius. So you need to use the right formula. The first thing you need to do is decide which formula you're going to use. They're asking for Celsius. So this is the formula you need to be using. 5/9, then the Fahrenheit, minus 32. Okay. Now, you can take this out. Okay. I'm just doing it step by step so you know what I'm doing. As you get better at this, you can go on directly and put it in there. So they give you the amount of Fahrenheit you had, so it's 34.5. Okay. And you're going to do this part first, the parentheses first, multiply by 5, divided by 9. And you're going to have to stop in the 10th position. So when you do that, the calculator gives you that 1.4 degrees Celsius. You stopped in the 10th position. And that's how we solve this problem. Let me erase this and go back to instruction. Okay? Hopefully this makes sense, but remember, you can always ask me questions. Let's see if I can make it smaller. Maybe not. Okay. Example 2.2 on page 42. That's going to be the last one for today, so it's not very difficult. It says, what is the boiling temperature of water in Kelvin? Remember that I said to you, you needed to memorize this kind of stuff. And then the second part to this says, the lowest temperature that has ever been recorded in the US is minus 80 degrees Fahrenheit. What is this temperature in Kelvin? And then we're going to do extra practice problem number 2. So today, all we have been learning is how to go from one temperature scale to another temperature scale, mathematically speaking, because you learn a lot of conceptual stuff, but in computation, that's what you learn. So let's imagine, let me go back to the board here. Let's imagine that you have memorized that boiling temperature for water is 100 degrees Celsius. Okay? You should have this memorized, and if you have not memorized it, you should memorize it. Then you know that the formula to change into Kelvins is the number of degrees Celsius plus that 273.15. And I said to you that this is not infinitively precise, so that needs to stop in the 100th position. Okay? So let me erase the place where the Celsius go. We're going to put the 100 in there. I'm going to put it in yellow. So 100 in yellow. Okay. And add it up. Put it in your calculator. What does it give you? It gives you 373.15. Correct? But let's think about this. Did they give you a temperature for the water? When they want you to memorize the temperature for the water, let me put it in blue. They want you to memorize it with 1 0 after the decimal point. And I forgot to write it down. It is Celsius. So that means that we need to stop in the 10th position. This is an addition. And the rules for significant figures when you have additions or subtractions have nothing to do with counting significant figures. It has to do with positions. So this one has 1 after the decimal point, the 10th position. That means that our answer needs to stop right here in the 10th position. Look at the next one over. 5 is big enough to round it up. So your answer is 373.2 Kelvin. This is your answer, okay? Because you need to stop in the 10th position. You always look at the next number coming up, see if it's big enough, 5 and up, round it up, and round up if you can. And then that's the answer for example 2.2. Now, the second part to the problem says the lowest temperature that has ever been recorded in the United States of America is minus 80 degrees Fahrenheit. What is the temperature in Kelvin? We don't have a formula that allows us to go directly from Fahrenheit to Kelvin, but we have one that goes from Kelvin to Celsius and one that goes from Celsius into Kelvin. So that's what we're going to have to do. We're going to have to first go from Fahrenheit to Celsius, and then from Celsius into Kelvin. Okay? It's always good to have a plan of action. So if this is giving you trouble, make yourself a little note of what you need to do. Well, what is the formula that allows us to go from Fahrenheit into Celsius? It's this one right here, 5 nines, the Fahrenheit, minus 32. Okay, we're doing the first step. So I know that I can put my minus 80 0.0 degrees Fahrenheit right here. Let me erase this so I can put that number in there. I'm going to put it in yellow. So I'm going to put my minus 80.0 right here. Now I can put this in the calculator. Going to give me a negative number. Then when I have this done in parentheses, I multiply by 5 divided by 9, and I get this number, minus 62.2 degrees Fahrenheit. Okay, so this is your Fahrenheit, but that's not what the problem wants to know. They don't want to know Fahrenheit, they want to know Kelvin. But now, so I have done this part. This is done. I'm going to do the next one in blue. Now I can go from, did I put silly goose? This is Celsius. Okay. I went from Fahrenheit to Celsius. Now I can go from my Celsius to my Kelvin because I do have an equation that allows me to do that. And you can write it down. Kelvin is your degrees Celsius plus the 273.15. And remember that these equations you are going to need to or memorize if you're going into science or keep in a formula page. So now I can go in, take this out and write down my value for my Celsius. And I found that in my previous step. So put that in the calculator. This stops in the 10th position. So that means that this is the least precise of the two values. This stops in the 100s. So my answer is going to have to stop in the 10th position. So when you do that, you get 210.95. That means I need to stop right here. I look at the next over. This is big enough to round it up. That becomes a 10. That means that this becomes 11. Okay, so 211.0 Kelvin is my answer. And that's example 2.2. Now you're going to do extra practice problem number 2. I'm going to give you the answer. Remember, I give you the answer. If you get it right, you move on. And if you don't get it right, then you check to see how it's done. But number 2, this gives you a chance to practice on your own without me doing it for you. Gives you a chance. So the answer they're asking for Kelvin is 394.3 Kelvin. You got this, you're done. Okay? And you move on to see what comes next. Which is me just telling you what you need to do this week. But if you didn't get this number, check to see how this is done. So the first thing you always do is read the problem really well. It's asking you to convert 250.0 degrees Fahrenheit into Kelvin. And remember what we said, we don't have a formula that allows us to convert Fahrenheit into Kelvin directly, but we can do these Fahrenheit into Celsius, and then from Celsius we can do Kelvin. So it's 2 steps. It's a problem that has 2 steps. That's all you have to do. You have the formula to go from Fahrenheit to Celsius. So that's what you need to do. Your Celsius is going to be the 5/9. I'm going to put it directly. You need your Fahrenheit next. So you put the 250.0 and minus 32. This is the formula that allows you to calculate Celsius from Fahrenheit. So you put the Fahrenheit right here. So do these in parentheses first, put it in the calculator, multiply by 5 divided by 9, and the calculator should shoot this number out to you, 121.1 degrees Celsius. Are we done? No, we are not done. We just have done this right here. We still have to do this part right here. We need to go from Celsius to Kelvin. I'm going to pick up a different color so I can do it here in the corner. But the formula for finding Kelvins is the Celsius, so the number we just found, 121.1, and you add 273.15. Now, this stops in the 10th position. That means your answer can only be as precise as the least precise, which is the 10th position. When you do that, it comes out to be 394 0.3 Kelvin, which is what you should find. And that is example number 2. Hopefully this makes sense. Now, this is the end of the first half of module 2, so we're plodding along. This week you're going to read the chapter, the first half of module 2. You are going to add to your notes. You're supposed to be taking notes if you need to. Work the examples again if you need to. Work through all the examples that you encounter as you encounter them, as you read the chapter, and remember to correct them one at a time. Your answers are at the end of the module. I don't want you to make the same mistake over and over, so correct one at a time so you don't carry that mistake with you in your head. Study for your conceptual weekly quiz. So you're going to have a quiz. Just check the link and take the quiz. That's the way I know that you have studied this week. Do all the labs assigned for this week. There's only one lab assigned. And you're going to have a test. You're going to have test 1 that's assigned for this week. So module 1, the test is due this week as well. I hope this makes sense to you. If not, you can always ask me questions when we meet virtually. I hope your week goes well. Bye.